Let's move on to the subject matter of today. I'm going to start with some questions and comments that people made because it leads us into the subject matter, which is Mr. Feynman, Dr. Richard Feynman, Dickie Feynman, okay? And so let's start with this. Paul says, physical, he says, relating to the body. Where did he get it from? He got it from, he just copied and pasted from the Oxford Dictionary. It says relating to the body as opposed to the mind. And it also says relating to things perceived through the senses as opposed to the mind. You know, talking about touch and see and touch. Famous see touch. They say mathematicians think that anything that you can see or touch is what an object is, what physical means. And that's not true. Okay, that's an irrational definition, because if you can't see or touch it, is it physical? For example, you know, the table the Klingon has on the other side of the universe, which you cannot see or touch. Is that physical? You say, well, he can see and touch it, or I can see and touch it if I travel over there. Well, that's not fair, because you're saying that until you run the experiment of seeing and touching, it's not physical. So you're going to wait for an experiment. Until then, a table is not physical. See the problem? Okay, so, but here's this fellow's contradiction. He says, physical presences are forms, okay? An object is a form which has physical presence. And then he tops it off, says, there are physical presences other than objects. See, we went all around in circles, okay? Yeah, I'd like for you to mention which physical presence, which is not an object, okay? Well, we'd like to know. Okay? The fellow just states that. He's saying, you know, an object is that which has form, which has physical presence, but there are physical presences which do not include objects. I don't know. He's talking about ghosts or spirits. I have no idea. Which again, if it's physical, and you're talking about see touch, right? Because that's what it is. Well, I don't know. He's got to explain that. Okay, another fellow questions the ropes, especially in regards to gravity. And he says, I don't know if your hypothesis asserts objects closer to each other have more connecting ropes. Okay? If so, what mechanism adds or removes connective ropes? And the mechanism is known as distance. And I don't mean the distance of mathematics, I mean, which is distance traveled. I'm talking about separation, qualitative separation. The closer two objects are to each other, since every atom from one object is connected to every atom of the other object through these ropes, the closer they get together, the ropes fan out. So you're not creating new ropes. You're not saying, oh, more ropes entered from, you know, outer space or whatever. No, what you're saying is the objects are already connected. And as they get closer to each other, you can see what's happening there. The ropes fan out. And it's that gradual fanning out, which is the acceleration of gravity. The closer they are, the more the ropes fan out, the faster you go, because of more and more ropes fan out. That's the mechanism we propose for gravity. That is the acceleration of gravity, or the mechanism of the acceleration of gravity. Here's the single thread, okay? See if I can get it here. No, I don't have it. Okay, anyways, we have a single thread. Let me put this other one here. See if this one is okay. I didn't check these out. No, I don't have either one. But anyways, what I wanted to say is that you have the single thread. That's our hypothesis. That's our assumption, that there's a single thread throughout the universe. This thread weaves every atom and every rope that connects any two atoms. So there's only a single thread. If we would take every atom and disassemble it, and disassemble every rope, we would end up with a single thread in the entire universe, a single closed loop thread. Okay, and the single closed loop thread, you know, when you weave it, you weave the atoms and the ropes that interconnect them. And so there are no more ropes that come out of nowhere and, you know, come in between two objects. That's not the theory. The theory is that as two objects approach each other, the atoms that are connected by these ropes, the number of ropes that connect these two objects is a fixed amount, because it's from one atom to another. And we're talking about hydrogen atoms. And we don't care if it's uranium 92 protons and electrons, right? 92 hydrogen atoms and 205 or 208 neutrons. Okay, we're talking about them coming together and the ropes fan out. So we're not creating new ropes. Okay, I just want to clarify that for those of you who are not familiar with the theory. Okay, and here we have another fellow. He says, how do we tell the difference between the blue stuff and the black stuff if it is both invisible and intangible? And this fellow proposed that the thread, the rope model, that's an ether. And I'm saying, no, it's not an ether because ether is a bunch of particles. And so I said, I put the challenge out there for anyone who can come up and tell me what the ether looks like. And he said, well, your ropes are an ether. I said, oh, is that true? And he drew it, and this is what he illustrated. And the problem here is that we have three things. We have the black stuff, we have the round white stuff there, the supposedly the atoms, I guess, and we have the blue connections, which apparently are the ropes, okay? And so he said, how do we tell the difference between any of these if we can't see them? And the issue is, it's not a question of seeing. The first thing we do in science is what they do in the mafia. We wipe out the witness. We kill the observer. There are no observers in science, in rational science. Observers exist only in mathematical physics, in the religion of mathematical physics. And so we have no observers. Here you have to tell the crowd what you mean by ether. And the guy says, phantom thread, ether. I don't know which one of those is the ether. Is it the white stuff, the black stuff, or the blue stuff? And he said, well, I can't see them. Well, you have to make them visible. In fact, you did make them visible. And so you have to tell me which of those three things is the ether. Right now, you can't say all three of them are the ether, okay? Because ether can only be one object if you're going to treat it as an object. If you're going to say that the thread is an object, okay? And, when I show the thread, I show a single closed loop thread. And in fact, this is what it looks like. Here it is. That's what I'm saying. It's a single object. Now, this object, as it twines around, turns into ropes and into atoms, okay? But here, this is showing something different. In fact, he shows that the blue stuff is separate, something different than the white stuff, because the blue stuff is all connected together, but it doesn't blend like in my hypothesis. It doesn't blend with the white stuff. Otherwise, he would have painted him white. And if we paint the black stuff white as well, then we have nothing. So the ball is still in his court. He's got to tell us what he means by ether. Okay? And if it's an object, we don't want you to define it. We want you to point to it and name it, illustrate it anywhere on the internet. Okay, here we have another fellow says, this theory is the best description of gravity yet with numerous evidence across all fields. Evidence. You should be less skeptical about it, even though this thought experiment might seem counterintuitive. Okay, also give Brian Greene, or Brain Green, I guess, a chance to explain the troubles of the Newtonian alternative. What is this fellow talking about? Well, he's talking about good old Brain Green, okay, Green Brain. And he just pointed out to this one episode of The Elegant Universe, which was, I guess, the biggest show that Brian Greene made, or at least one of them. And in there, he says, string theory says that we may be living in a universe where reality meets science fiction. Oh, my God. That's a bad way to start a scientific theory, right, or explanation. Says a universe of 11 dimensions. 11 dimensions. I mean, I don't know how much beer this guy drank, but you can see him drinking there, right? With parallel universes right next door. Okay, and so they have all these parallel universes. You can see all the magic stuff he put out there. He's saying this is physics or science or whatever. String theory is surprisingly simple. Okay, it says that everything in the universe, from the tiniest particle to the most distant star, is made from one kind of ingredient, unimaginably small vibrating strands of what? Energy. Vibrating strands of energy, which he calls strings. Okay, well, what can I say? There's no such thing as energy if we knew what it was, and we're going to be discussing that with good old Dick Feynman today. But question is, this guy's talking about many dimensions. He's saying that it's very simple to understand. Is it? And he shows us magic tricks, unexplained magic tricks. He just says, we don't know the cause, we don't know the theory, we don't know the explanations, physical interpretations, we don't know the mechanisms, but it is so. Okay, so no, not much to learn from good old Brian Greene. Another fellow, more or less the same thing, he points to Dr. K. He says, here's Professor Alex Kantarovich, okay, I'll call him Dr. K, who goes against definitions themselves in maths. I thought it might interest you for one of your various points, okay, and this is what good old Dr. K has to say. He says it on the Veracitum program or series of Derek Miller. And they're referring to Euclid's definition of geometric figures, point, line, and plane. And good old Alex K., this professor, he says, don't give me a definition that's going to have an infinite recursion. Okay, so he doesn't want you saying, defining and then saying, and this definition of this word is this, and then goes and tries to define every word of that definition as well. So he doesn't want an infinite recursion. And Veracitum asks, are the definitions a bad idea? And so what does K say? He says, you shouldn't have definitions. You should have undefined terms. Now, this is a professor, okay, who's saying this. So he says, you got to have undefined terms. In fact, to this day, point, line, and plane, they remain as undefined terms, and these point, line, plane, they remain undefined. They have no way of defining them, admittedly, okay? So all these people who teach geometry say these are undefined terms. He says, I'm not going to tell you what a point is. I'm not going to tell you what a line is. I'm not going to tell you what a plane is. All I'm going to tell you is what the postulates are that they're assumed to satisfy. It's the relationships between the objects that's important, not the definitions of the objects themselves. Well, poor old Dr. K did not realize that, you don't define objects, okay? You point to them. And so you define concepts. And point, line, and plane, what are they? They're called what? Geometric figures, right? So if it's a geometric figures, you're not going to define it. You're going to point to it. And there, just so I educate Dr. K or Professor K there, not to compete with Kevorkian, who was Dr. Death, right? Also Dr. K. But Professor K should learn that, there you have the pictures. You have a point, you have a line, and a plane. What is a point? Well, you can see objectively what's coming out of the screen into your eyes. Now, maybe you're blind. Maybe you shot up today and you can't see very well or think very well. But I'm telling you, what's coming out of the screen is objective for everybody on planet Earth. Okay? Whatever you interpret is a subjective. But what's coming out of the screen is for the word point is a 2D dot. That's what's coming out of the screen. What's coming out of the screen for line is a 2D elongated rectangle. And what's coming out of the screen for the word plane is a 2D square. Okay? So they're all 2D. They're all two-dimensional, these objects. In fact, there's no object that is neither 2D or 3D. All objects are 2D or 3D. There's no object that is 1D or 0D or 4D and above. Okay? And so why do they say that the point is 0D? Why do they say that a line is 1D? Well, because they're referring to location and itinerary respectively. Okay, so they say, well, location. Well, why did you put a dot? Why are you pictorially representing the word location with a dot and calling the whole shebang a point? Why are you representing an itinerary with a line, and it could be a dotted line because that's the way they usually put it, because each dot is a location, right? Meaning they're talking about an itinerary, and they're saying that's 1D. Well, an itinerary is not any D at all. And a location is not any D at all either. They're not 0D and 1D. An itinerary has nothing to do with dimensions because it's not a physical object. So you either talk about the figure, the geometric figure, or you're going to be talking about, concepts, dynamic concept like itinerary or static concept like location. Okay, and here, just to rub it in a little bit, is this what we're going to do here? We're going to represent love with a heart. Is a heart 0D, zero-dimensional? We're going to represent intelligence with a brain. Is a brain one-dimensional? Are we going to say that grace is represented by God, a three-dimensional being? Is that what we represent concepts with, pictorially represent them with? So again, you cannot represent concepts with objects. That's okay if you want to do a little poetry, little art, no problem. But don't bring it into science. Don't bring it into physics and tell me that a heart represents love or that a point represents location. Okay? And this is where the problem is. That's why they say we can't define it. Of course you can't define it because you're confusing concepts with objects. You're trying to represent a concept such as location with a dot, and you're calling the whole thing a point and think you can get away with that. Not in physics. Point is 2D or 3D. You can have a ball represented, no problem. But you cannot say that that represents location. Location has no pictorial representation. Okay, and the final issue here, a little article that came out, I thought I'd rub it in there. It says, see the first astounding images from the Euclid Dark Matter Telescope. Dark matter telescope? What the hell is that? I thought dark matter was invisible and intangible, and these people have a telescope? The Euclid telescope to what? To see dark matter, I guess. That's what telescopes are used for. And yeah, the issue here is that these people don't look at dark matter. They're looking at the same thing for which they don't need to see any more than what we see out there with a common eye, and that's, you see the visible stuff. So with a telescope, okay, so you can see farther out in space, meaning you can see maybe the galaxies and even some of the stars of the galaxies. You can see the visible stuff. You're never going to see dark matter because by definition, dark matter is invisible, intangible, right, also. And so, you need no telescope for that. What you need is to make a proposal, what you think dark matter is, and make it visible to the eyes. Just make a hypothesis, an assumption, supposition, and say, look, this is what I think dark matter is. And you can represent it with particles as they do, no problem. But then you have particles. And you don't need a telescope for that. You just need to make an assumption of what you think dark matter is. Okay? And so you can say, oh, dark matter is a bunch of particles. And they weigh a lot and they're small and whatever. You can describe that. And then once you do that, you got to explain how those particles create the effects such as the galaxy rotation problem, which is means that they're sprinkled on the outside of a galaxy only, preferentially, for some reason. I don't know why. You got to tell me. And they're sprinkled outside the galaxy, and just encapsulates the galaxy. Because otherwise, you cannot explain, or mathematicians cannot explain, why the stars on the outside travel faster than those on the inside, or at the same speed or faster. Pluto doesn't travel faster than Mercury around the sun. It's the other way around. And in the case of stars, it is that Pluto would be traveling faster than Mercury around the sun. And you say, well, how can that be? Well, we can explain it. We put more mass, more matter outside of Pluto, and that would explain why Pluto can go faster than Mercury. Okay? And so they say that's what's happening to a galaxy. So they sprinkle this stuff in there and they say there's all this matter which we cannot see and which is translucent, transparent, invisible, whatever, because you can see the stars in the background right through this dark matter thingy. And so even if you put dots in there and say, okay, here we have all this matter, it weighs a lot, no problem. But then the question is, how with that do you produce the galaxy rotation problem, meaning that stars on the outside travel faster than those on the inside? You still have to answer that question, the mechanism. And even particles you cannot explain. Because in order to explain it, you would have to show how this particle is in physical contact with a star. Connection, physical connection of some kind. The ropes. Yeah, no, there is no such thing as dark matter because you don't need dark matter to explain the galaxy rotation problem. This is very simple. And the first thing you got to explain, why don't the stars on the outside, right, especially those on the outside, but all of them for that matter, but especially those on the outside, when the galaxy rotates, why don't they go flying out, out of the galaxy? That's all you got to explain. And the only way you can explain it, the only way you can rationally explain it is if that star somehow is connected to the center of the galaxy, meaning to all other stars in the galaxy. Only then you can explain why the whole thing rotates like a single platform. You're on the carousel, on a merry-go-round, and the whole thing travels at the same speed, same time. The horsey on the inside and the buggy on the outside, they travel at the same rate because the whole platform is turning at the same time. Why? Because they're all connected. They're all on the same platform, and that's the case with galaxy. It rotates. The ones on the outside almost practically at the same speed as those on the inside, or faster, meaning they travel at the same rate around. Why? Because they're all connected. Then you can explain it. But if they're not connected, the first thing you have to explain is, why doesn't this star just go flying out of the galaxy? And it's very simple. So connection explains it all. And to top it off, same publication, right? So dark matter may have come from a second, darker Big Bang. These people are so clueless. They don't know what to invent anymore. They have to invent a second Big Bang and to try to cover all the holes in their theories. So, you wonder about these mathematicians. It's like they have nothing else to do than come up with all this nonsense to try to cover the holes in their theory. So they create dark matter, dark energy, Big Bang one, but black holes and wormholes and so on. They have to create all these non-entities, all these spirits. In fact, spirits are probably easier to imagine than concepts such as dark matter and dark energy to cover their holes. That's the only reason these things were ever created. And the problem here, this is what should shock you, is that you have all these mathematicians on planet Earth, almost in every university's research center, professionals, etc., and they're studying what? Black holes and dark matter and dark energy. That's where your funds are going. Directly or indirectly, that's where your funds are going, into the study of inexistent stuff. They're studying souls and spirits and conscience, souls going to heaven, that kind of stuff. It's even worse because, again, they're only dealing with abstract concept, mathematical concepts. And so think about that next time you pay your taxes. Coming up. Okay, so how does this lead to Mr. Feynman? Well, because he was a supporter of all this stuff. And Richard Feynman, he was a very popular teacher. Okay, very popular teacher because he was charismatic. He told jokes and so on. And here you have just an image, so that you can see why he was kind of popular with the students. He would tell jokes and talk in a friendly and also in a straightforward manner about stuff. And people like that because they say, I can finally understand this teacher instead of some of these other professors or instructors who went off into math and stuff like that. This fellow just tells it straight out like the way it is. Okay, that's why he became so popular. Okay, and good old Dick here, he won a Nobel Prize. Okay, here he is. He won a third of a Nobel Prize, right, for developing quantum electrodynamics, otherwise known as QED. What was his contribution? Well, primarily this space-time diagram. Okay, he says you got two electrons, and they send one of these virtual photons, virtual quantum, whatever, and they interact, and that pushes the two electrons away. Okay, and so this is it. This is primarily what he contributed. He got a Nobel for this, 1/3 of a Nobel. Okay, they gave him a third of a coin. Okay, fine. So this is his contribution. So how much did he know about QED? I mean, this was his down his aisle. This is what he worked on. This is what he studied. This is what he contributed to quantum mechanics, science, if you can call it science, physics. And he says, well, you understand what I'm going to tell you. You think I'm going to explain it to you so you can understand it. No, you're not going to be able to understand it. You see, my physics students don't understand it either. That is because I don't understand it. Nobody does. While I am describing to you how nature works, you want to understand why nature works that way. In other words, he had no physical interpretation, which is what physics is all about, which is what we wanted to always know or understand, right? But you see, nobody understands that. I can't explain why nature behaves in this peculiar way. The theory of quantum electrodynamics describes not explains, but describes nature as absurd from the point of view of common sense, meaning he cannot explain it mechanistically. Why? Because he's talking about particles. That's why. You cannot explain with particles, discrete particles, how the universe works. And it agrees fully with experiment, which we don't care anything about. So I hope you can accept nature as she is, absurd. No, we cannot. We can accept that you're ignorant. That would have gone a long ways to helping people understand that the mathematicians don't know squat. That would have been great if he would have said, look, we're all so ignorant. He said it in softer terms, but I would be a little more adamant, because today people say, oh, we know it all. And you say, what do you know? Can you explain gravity? Oh, you're talking about a physical interpretation? That's philosophy. And they brush it aside. And they say, let me tell you about my equations. The problem with equations, that's a description, as good old Dickie just said. Okay? But the problem is that, that's not science. That's like saying you measured a table and you measured it to be 1 meter, and the other guy comes over and says, no, I've got a better measurement. I got 1 meter and 1 micrometer, so I'm a little more accurate than you. Okay, so you measure a table. Is that science? Yeah, measurement and followed by an equation? Or is it explaining something like gravity? Why, a famous trick here, why the pencil falls downwards, not to the ceiling. That's what you got to explain. And the only way to explain that is by making visible the invisible. You have to show me what is in contact with a pencil. And if you say, well, nothing. Why? Nothing, because, I can't see anything above or below, so there's nothing there. Well, because you're talking about seeing and touching. And that's not what a thing is. A thing is that which has shape. So you got to draw the shape that you think is connecting the pencil, or coming in contact with a pencil, because, maybe something's pushing from above, something's pulling from below, whichever, I don't care. But you got to show me what's in contact with a pencil, and for that you have to make the invisible stuff, the mediators, visible so that I can understand your mechanism. That's what it's all about. And they've never done that, because they say, oh, an object's that which I can see and touch, and I can't see and touch anything there above or below, so there's nothing there. But if you say that there's nothing there, if you're talking about action at a distance, you're talking about black magic, you're talking about witchcraft. That's the problem. Okay? That means you're going to invoke black magic and say it's done by magic. Mother Nature works by magic, and that's why these people like Richard Feynman concluded that QED, or quantum in general, cannot be explained. Nobody understands it. And just in case, let's make sure that that's the case. He said quantum mechanics is the description of the behavior of matter and light in all its details, and in particular of the happenings on an atomic scale. Things on a very small scale behave like nothing that you have any direct experience about. They do not behave like waves. They do not behave like particles. They do not behave like clouds or billiard balls or weights or on springs, or like anything that you have ever seen. We choose, and then he talks about, why they concluded with this. He talks about the slit experiment. He says we choose to examine a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. We cannot make the mystery go away by explaining how it works. We will just tell you how it works. In other words, he's going to describe, right? One might still like to ask, how does it work? What is the machinery behind the law? No one has found any machinery behind the law. No one can explain any more than we have just explained. No one will give you any deeper representation of the situation. We have no ideas about a more basic mechanism from which these results can be deduced. And the whole problem is really comes down to the fact that, like he said, light cannot be a particle and light cannot be a wave. It's neither. And they insist on doing it with particles and with waves when he's telling you it ain't one or the other. So we got a contradiction. Instead of going to the basement, dark basement, and thinking hard and proposing assumptions, brainstorming assumptions, the guy says it just ain't particles and it ain't waves. Okay, so what is it? It says nothing like you ever imagined. Well, have they tried this? A rope. This you can imagine. In fact, I'm showing it to you right now. And a rope is neither a wave nor a particle. And now we have a different proposal here, a different universe, right? Okay, so he continues saying, the quantum mechanic behavior of things is quite strange. Yeah, because they're trying to do it with particles, in fact, which are not particles anyways, because the so-called particles of quantum mechanics are really numbers. They're concepts, and they're trying to move concepts. So when they tell you that they have a particle accelerator at CERN or at SLAC or Fermilab or whatever, they're not talking about particles. What they're accelerating is numbers. What they're doing is they're saying something accelerated, and we're going to call it a particle, and we're going to represent it with a number because we're interested in determining what the energy was and what the mass is, what the charge is. They're going to go into numbers and units. They're not going to be talking about a ball. Okay, and that's important that you know or that you understand that. Nobody has an everyday experience to lean on to get a rough, intuitive idea of what will happen. We could either describe what can happen in a rather rough physical way, meaning they can't describe it at all, right? Telling you more or less what happens without giving you the precise laws, meaning they cannot tell you anything about what's in that invisible world, laws of everything. Or we could, on the other hand, give the precise laws in their abstract form. But then, because of the abstractions, you wouldn't know what they were all about physically. Yeah, that's the point. They're not doing physics. That's the problem with these people. They're not doing physics. Quantum mechanics is not physics. It's just a bunch of abstractions, mathematical abstraction. That's all it is. The latter method is unsatisfactory because it is completely abstract. Yeah, tell me about it. And the first way leaves an uncomfortable feeling because because one doesn't know exactly what is true and what is false. Yeah, in science we don't care what is true or false. We care about explanations, mechanisms. Okay, we are not sure how to overcome this difficulty. Okay, and then what is his conclusion? Okay, here, let me remove this. He says the following. He says, I think I can safely say that nobody understands quantum mechanics. Do not keep asking yourself if you can possibly avoid it, but how can it be like that? Nobody knows how it can be like that. The more you see how strangely nature behaves, the harder it is to make a model that explains how even the simplest phenomena actually work. So theoretical physics has given up on that. They've given up on that. Okay? In other words, nobody does physical interpretations. And the worst part is that they dismiss that as philosophy. They say, we do equations. But then it's my $1 million question. If they just do equations, if it's not part of their job description to give you a physical interpretation, if they don't do philosophy of physics, philosophy of science, whatever they want to call it, if they dismiss that as philosophy, if it's not part of their job description, why did they even attempt to give you a physical interpretation? Why didn't they just stay with math and say, this is what we do. We do equations and math and describe. No problem. I have no problem with that. It's when they cross the line into physics and they say, let me tell you how the universe works. Okay, how does it work? Well, you have all these particles and they do all this magic. But you cannot explain it. Yeah, but that's philosophy anyways. We do math. We got a contradiction. Because if you don't do physical interpretations, don't do them. Don't do them. Don't jump the fence and try to do physics when you're not doing physics. When you can't do physics because in the end, you say, well, it's philosophy anyways. That's not part of our job description. That's where the problem is. These people are telling you they know how the universe works through their math, right? Because otherwise their math would be completely irrelevant if they cannot tell you how the universe works, how gravity works, how light does its magic. They cannot explain that in a rational manner. Then their equations are worthless. That's why they try to give you a physical interpretation. When you call their bluff, they jump back the fence and say, well, we don't do that. That's on the other side of the fence anyways. That's philosophy. That's the problem. That's where the contradiction is. Okay, so what does he have to say about light? Okay, here it is. Neither the wave viewpoint nor the particle viewpoint is correct. Aha. We would always like to present things accurately or at least precisely enough that they will not have to be changed. But when we try to talk about the wave picture or the particle picture, both will change. Therefore, what we learn will not be accurate. We will deal with some half-intuitive arguments. In other words, he has no intuition, meaning he has no proposal for what light is, because that's where you got to start. Okay, here we say, here it is. That's what light is. Light is torsion along a physical entity, not a concept, not a mathematical abstraction. It's a physical object that, that binds any two atoms. My fists here serve as atoms, hydrogen atoms, okay? And what light is, a torsion. Now we have a torsion. Now we can explain why light is so fast, because a torsion wave is faster than any transverse or longitudinal wave. Okay, or any kind of wave for that matter. You have one-dimensional, two-dimensional waves. This is a 3D wave. Okay, so it's a torsion, and it's the fastest thing you can imagine. Nothing is faster than a torsion wave out there. Okay, torsion is fast because the object is already connected at two ends to the two atoms. So nothing has to travel. All you do is torque, and the signal is what is detected by the other atom. It's a thump that it receives. Okay? And that's why light is so fast. Now we can explain the speed of light, why it's so fast. Okay? But yeah, if you're going to try to do it with particles, not only are they one way, whereas a torsion works two ways, right? The standard wave, whether you take the standing wave or any kind of wave for that matter, other than the torsion wave, you have a one-way wave. One-way particle, one-way wave, and you cannot explain how the universe works with any of those two. Okay, what does he have to say about energy? Well, that's very quick. Here I've said it many times. It is important to realize that in physics today we have no knowledge of what energy is. Well, good old Feynman didn't realize that energy was not a what, and neither has any mathematician since then. Energy is not a what. Energy is a concept. What's are objects? An object is a what. So you can point to it, but you can't point to energy, because energy is a mathematical concept. And he never realized that. So he's trying to figure out what is energy. I thought you didn't do physical interpretations, Dickie. Okay, and then energy, the capacity. That's what it is, the ability. That's how it's defined. And so, yeah, the capacity is not a physical object. Neither is the ability. And then what did he have to say about gravity? And remember, quantum mechanics has no idea what gravity is. So he says, what is gravity in his lectures, right? What about the machinery of it? All we have done is to describe how the Earth moves around the sun, but we have not said what makes it go. Yeah, that's what we want to know. Newton made no hypothesis about this. He was satisfied to find what it did without getting into the machinery of it. It's not that he didn't, Newton tried to figure out how it works, why it works the way it does. In other words, he wanted to figure out the mechanism. But he was thinking of particles also. He was an ether guy. He believed in the ether, particles, bunch of particles, and he could not explain it with particles. So he says, it just blows my mind how this could be happening. Yeah, if you propose particles, you cannot explain it, and Newton couldn't explain it, but he says, he did not delve upon that. Yeah, he did. He did, but he just couldn't explain it. And neither can good old Dickie here, right? So no one has since given any machinery. Yeah, they've given a machinery, not in quantum, but in general relativity, but it's an irrational one. They're saying that there's this thingy, concept, mathematical concept, called space-time, and it bends. A concept that bends. Man, that's deep. A concept that bends, it's like love bending, intelligence bending, data bending, It is characteristic of the physical laws that they have this abstract character. No, they don't have this abstract character. Only in mathematics do they have abstract characters. The law of conservation of energy is a theorem concerning quantities that have to be calculated and added together. Again, they're talking math. They're not talking about physics. With no mention of the machinery, right? Because machinery is physics, right? And likewise, the great laws of mechanics are quantitative mathematical laws for which no machinery is available. Yeah, because they have the math, the equation, they have the measurements, but they don't have the proper assumptions about the invisible mediators or objects that mediate, the transactions, the phenomena. Why can we use mathematics to describe nature without a mechanism behind it? No one knows. Yeah, if you don't have the right assumption, the right hypothesis, as it's called, the right objects, the right mediators, you're not going to explain it. You're never going to be able to explain it. Okay, so one fellow asks about a question related to good old Feynman, says, we assume that the electron is a ball, indivisible, that it is not composed of other objects, but that it is unique and uniform. In other words, what he's saying is that it's made of a single piece, in short. That's how we say it in physics. It's made out of a single piece, period. This ball spins on itself. They call it spin. This ball turns and turns, but it always shows the same face, the same surface, properties, the same side. I wonder if it turns or if it is still. And so good old Dickey also, talked about spin, okay? And here it is. He says, spin should not be conceptualized as involving the rotation of a particle's internal mass, as ordinary use of the word may suggest. Spin is a quantized property of waves. So it's a wave that is spinning. So it's not a ball. That's the first one, The very earliest models for electron spin imagine a rotating charged mass. Yeah, mass is also a concept, so we don't have mass. Mass cannot rotate. A ball can rotate, not a number, not a mathematical concept. But this model fails when examined in detail. No kidding. The required space distribution does not match limits on the electron radius. The required rotation speed exceeds the speed of light. See, that's part of the problem why they cannot explain this. The classical analog for quantum spin is a circulation of energy. Energy circulates. I mean, what is it? Smoke? What is this energy thingy? Or momentum density in a particle wave field. Spin is essentially a wave property. As the name suggests, spin was originally conceived as the rotation of a particle around some axis. Yeah, that's what we think spin means, right? Historically, orbital angular momentum related to particle orbits. While the names based on mechanical models have survived, the physical explanation has not, right? Because you can't rotate numbers. You can't spin numbers or, quantities or abstractions. Quantization fundamentally alters the character of both spin and orbital angular momentum. Since elementary particles are point-like, self-rotation is not well defined for them. Yeah, what is the problem with this spin thingy that quantum has? Well, again, first, I cannot imagine how they can conceive of a wave spinning, especially a transverse wave, because a transverse wave is made of two fields, the light is made of two fields 90 degrees to each other, and each field is just made of vectors. So what are we talking about? We're talking about numbers that are rotating. That's the problem. That's where it starts. Now you need a physical object. You can say that a ball spins. You can talk about this spinning, okay? But what's the problem? To answer this fellow's question, if this is made out of a single piece, you cannot say it rotates. Because in order to rotate, you need at least two things. You need a center point and an edge point. If this is made out of a single piece, meaning very small, tiny thing made out of a single piece, you cannot imagine it rotating. You cannot conceptualize it rotating, because the only way we can imagine something like that happening is if the point on the outside compares against the point on the inside. And if it's made out of a single piece, you're going to try to imagine that as a ball made out of particles, where you have two particles and one is rotating around the other. So you cannot have spin in an object made of a single piece. And no one in mathematics ever resolved that, and that's why they use the word spin. They illustrate spin as spinning, as a top spinning, but then they tell you that's not spin. What do you mean? Is spin or is spin not spin? And they say, well, it is spin, so we illustrate it that way, but don't take the analogy so literally.